Hi everyone, today we are going to cover sections 12.4 and 12.5, the brainstem and the cerebellum. So our goal for section 12.4 is to identify the three major regions of the brainstem and noting the functions of each area. So the brainstem is going to consist of the midbrain, the pons, and the medulla oblongata, made most famous by Adam Sandler in The Waterboy. The brainstem is similar in structure to our spinal cord, but contains nuclei embedded within the white matter. So it's going to control our automatic behavior that we need for survival. So think of the things that we absolutely have to do to survive. They're going to be controlled by the brainstem. So they're going to contain fiber tracts that connect the higher and the lower neural centers. So these nuclei are associated with 10 of the 12 pairs of cranial nerves. So the cranial nerves do everything from controlling our eye movement to allowing us to taste, to chewing, to making muscles of expression like smiling, frowning, acting scared, making the scared face. So we'll talk about a couple of those as we move on. I want to go back to this slide to show you exactly what we're talking about when we look at the midbrain. So we just covered the diencephalon in the last unit. So we have our midbrain here. We have the pons, which is kind of cut open right now, and the medulla oblongata. So you can see these yellow tracks. Those are going to be our cranial nerves coming off of the medulla oblongata. Okay, so if we were to actually look at a human brain, here's where we're talking about. So this midbrain is this region right here. Our medulla oblongata is right as it kind of descends down into the spinal cord. And then the pons, midbrain, pons. We can also see these small little tracks right here. Those are going to be our cranial nerves. So starting with the midbrain, it's going to be located in between the diencephalon and the pons. So these cerebral peduncles, they're two bulges that contain pyramidal motor tracts. So they're kind of what holds up our cerebrum. Okay, we also have what's called the cerebral aqueduct. Just by its name, you can imagine that it circulates fluid. So here it's going to be running through the midbrain that connects our third and our fourth ventricles. We also have this periaqueductal gray matter, which is nuclei that plays in a role in suppressing pain and also in our fight or flight response. There we go. So these are going to also include the nuclei that control our cranial nerves 3 and 4, so our oculomotor nerve, which basically just allows us to see and to be able to read. It also controls eye movement and our pupil constriction. And our trochlear nerve does a different kind of an eye movement. So one moves our eyes up and down, and one moves our eyes side to side. So our midbrain, the nuclei is going to be scattered throughout white matter. So we have what's called our corpora quadrigemina. So these are going to be protrusions from the back. They contain our superior colliculi, which is a vision reflex center. Coordinates our head and eye movement when we visually follow a moving object. So this could be conscious, it could be unconscious. I'm sure you've unconsciously, watched someone walking past, not on purpose, but it just was an unconscious movement. So these are also going to be our visual reflex centers. The inferior colliculi is our auditory relay center. So our responses to sound. If you saw, or I know we've all been there, where the classroom door opens and you reflexively just look in that direction, because that's how we respond to the sound. It also has what's called the substantia nigra, which is functionally linked to our basal nuclei. So Parkinson's disease is thought to be a degeneration of this area, so something we can link specifically to a condition. We also have what's called the red nucleus, which is a relay nuclei for some of our descending limb flexion motor pathways. So think about limb flexion, so providing this movement for us. So here we are taking a cross section, as you can see, of the brainstem. So we have that red nuclei here, the substantia nigra here, and then we have our gray and white matter surrounded in there as well. So the pons actually means bridge in Latin, which makes sense because it's going to be the bridge between our midbrain and our medulla oblongata. It is composed of these conduction tracts, so the longitudinal fibers connect the higher brain centers and the spinal cord to one another, and then we have these transverse fibers that relay impulses between the motor cortex and the cerebellum. So the cerebellum we're going to get to in just a second, where movement patterns are established, fixed in order to reduce accessory movement, and where those patterns are stored. So the pons is the origin of cranial nerves 5, 6, and 7. So our trigeminal nerve gives us sensory information from our face. It also controls the muscles for chewing. So if you had an injury to your trigeminal nerve, you wouldn't be able to chew. Our abducens also does eye movement. If you can remember what the ABD prefix means, it's going to do side-to-side movement, so abduction of our eyes. And finally, cranial nerve number 7 is our facial nerve. So this is has a two-parter. It does sensory taste, so allows us to taste, but it also controls the muscles of our facial expression. So it has a motor and a sensory component, so allowing us to do things like smile, frown, like pucker your lips, those kinds of things. So if I'm ever doing a concussion evaluation on the sidelines, we'll have them do that. Can you smile for me? Can you frown? Can you stick your tongue out? To make sure that these facial nerves, our cranial nerve number 7, is intact. Some of these nuclei are going to also play a role in our reticular formation. So if you remember, that's what helps us maintain our normal rhythm of breathing. So pretty important. So our medulla oblongata kind of blends into the spinal cord at the foramen magnum. So from our skeletal unit, the foramen magnum is a large hole at the base of our skull that fits our spinal cord. So kind of serves as an intermediate between our spinal cord and our midbrain. So this is going to contain our fourth ventricle. This is a continuation of that central canal of our spinal cord. It contains the choroid plexus, which is a capillary-rich membrane that actually forms our cerebral spinal fluid. So the choroid plexus is really important for this. If we didn't have that cerebral spinal fluid, we wouldn't have that cushioning and the nutrition for our brain. So the medulla oblongata has some really specific structures. We have what are called pyramids. So these are two ventral longitudinal ridges formed by pyramidal tracts from the motor cortex, so involved in movement. We also have the decussation of the pyramids, so the point where the pyramidal tracts cross over to the opposite side of the body. So this explains why, our right side of our brain controls the left side of the body and vice versa. We have something interesting, which they're also called olives, because they look exactly like olives. So they're swelling caused by the underlying inferior olivary nuclei that relay stretch information from muscles and joints to the cerebellum. So if you've ever been put in a position where your joint feels like it's really hyperextended or it's uncomfortable, this is what is going to send information back to our brain, indicating that there's too much stretch going on at the joint. So then our functional way to correct that will be to activate the muscles on the flexion side of that joint to bring it back into a more comfortable position. So this is going to control our cranial nerves 8, 9, 10, and 8, 9, 10, and 12. So we're going to skip 11. So our hypoglossal nerve is basically, it controls the muscles of our tongue. So it allows you to stick your tongue out. Those of you that can roll your tongue is going to control tongue movement. Our glossopharyngeal nerve also has two components to it, so a sensory and motor. It allows us to taste. It also controls the muscles that are needed for swallowing. So that'll be another thing I would have someone on the sidelines do is, can you swallow? Just to make sure that that nerve is intact. Obviously, if it wasn't, that could be really life-threatening. Our vagus nerve is cranial nerve number 10. So whenever I was teaching the vagus nerve to my classes, I would teach them, think of Las Vegas. When you're partying, you're having a great time, you're doing like a lot of yelling, so it is involved in speech and also motor functions of our glands, our digestion, heart rate. So it's really, really important as well. And the vestibulocochlear nerve, if you can put some of those root words together, obviously includes our cochlea in our inner ear, and is going to be responsible for hearing and balance. So again, a sensory and motor component to both of those. So our medulla oblongata, the functions of our medulla oblongata, it's an autonomic reflex center. So again, nothing that is voluntary. So many of the same functions, it has many of the same functions as the hypothalamus. So the hypothalamus is going to relay instructions through our medulla. Now, the functional groups of medulla include the cardiovascular center, which is going to adjust our force and rate of heart contraction, and the vasomotor center. So, vaso and motor, so blood vessel muscle, adjust the blood vessel diameters for pressure and regulation. So, whether it constricts our blood vessels or whether it opens and enlarges them. It also contains the respiratory center, so how we generate a respiratory rhythm. It controls the rate and our depth of breathing. And it also controls some other interesting things that we do, such as vomiting, hiccuping, swallowing, coughing, and sneezing. So moving on to section 12.5, the cerebellum. So our goals for section 12.5 are going to be to describe the structure and the function of the cerebellum. This is one of my favorite parts of the brain, mostly because it is what controls our skeletal movements and how we make smooth and precise patterns. So this is going to be located in the back, just sitting underneath our occipital region of our brain. So it's going to input information from the cortex, the brainstem, those sensory receptors. So including a lot of different elements to provide coordinated movements of skeletal muscle. So it also happens to play a major role in our balance, which those of you that play sports or play an instrument know that balance still plays a very large part in all of the things that we do motor-wise. So we have what's called a cerebellar hemisphere. So they are bilaterally symmetrical. So they are both symmetrical and contain this worm-like section in the middle called the vermis. So the folia, so we talked about gyri and sulci earlier when we talked about the cerebral hemispheres. So our cerebellum has the same things. It's very, it has these grooves and gyri. They're called folia in this case. And we have three lobes to our hemispheres. We have an anterior, posterior, and a flocculonodular. There we go. So this is going to contain a thin cortex of gray matter with a very distinct tree-like pattern on the inside. So this is going to be called our arbor vitae, which means tree of life. And you'll see how it looks like it has branches coming out here. So here we have our anterior lobe. Our cerebellar cortex is going to be this inside section here. So this arbor vitae, you can see, kind of has a branching tree pattern of white matter. We have our posterior lobe here, and then our flocculonodular lobe right there. Oh, one quick thing you can see too, it's really close to our medulla oblongata, and then we have these cerebellar peduncles too that we'll talk about here in just a second. So these guys right here. Okay. So if we look at an actual human brain, you can see that arbor vitae is really pronounced and does make a branching tree-like pattern. Okay. So if we actually take a look at our cerebellum kind of from behind, this vermis is that area that's going to connect the two, and you can see they're symmetrical, so both sides look exactly the same. Yeah. So we also have what's called Purkinje fibers. So they originate in the cortex and they synapse with the cerebellum, so sending messages. We also have, just like we had in our cerebral hemispheres, the homunculi, or the little man, that is connected to a specific area of the body. We also have a cerebellar homunculi. So before I show you this, let's just go over this real quick. The medial portions influence the motor activities of the trunk specifically, and girdle muscles. Stop doing that. There we go. The intermediate parts influence the distal part of our limbs and skilled movements. So arms and legs, distal part of the limbs, skilled movements. The lateralmost parts of each hemisphere integrate that information from the association areas. So remember, our anterior and our posterior association areas of the cerebral cortex. And they seem to play a role in planning movement, so not necessarily carrying them out, but how we plan them, how we expect things to go. And the flocculonodular lobes receive that input from the equilibrium apparatus in our inner ears and adjust our posture to maintain balance. So if you've ever been off balance, trying a new I don't know, like a jump shot, because we're all watching The Last Dance right now. So it's going to help us to figure out where we are in space and orient ourselves to make this a more smooth and controlled movement. So here's our cerebellar homunculi, little guy. So you can see the anterior lobe and what it can it controls, and then our posterior lobe and what it controls. We also have cerebellar peduncles. So all of these fibers are ipsilateral. So ipsilateral is going to mean to and from the same side of the body. So these don't cross over. The right side doesn't control the left and vice versa. It's going to stick to its own side. So we have 3 paired fiber tracts that connect the cerebellum to our brainstem. So we know the brainstem is important because that's where information is coming from, sensory information, and then the motor output connects to the same place too. So our superior cerebellar peduncles connect our cerebellum to the midbrain. So this is going to carry instructions from the neuron to the cerebral motor cortex. Our middle cerebellar peduncles connect the pons to the cerebellum. So this is going to be telling the cerebellum the voluntary motor activities that are going to be initiated by that motor cortex in our cerebral hemispheres. And then finally, the inferior cerebellar peduncles are going to connect the medulla to the cerebellum. So this is going to give us sensory information from muscle proprioceptors throughout our body and the vestibular nuclei in the brainstem. So when we talked about those muscle proprioceptors, so how much stretch does it have? How much pressure is being put on it? And then that vestibular nuclei is going to give us information about position in space and imbalance. Okay, so our cerebellar processing. So the steps to fine-tuning a motor activity. So think about anything that you might do, whether it's shooting a free throw or playing the piano. Those things first initially started as voluntary control, right? But the more that you do it, the less it becomes volitional, and it just becomes automatic muscle memory. So how that happens is the cerebellum is going to receive impulses from our cerebral cortex of the intent to initiate this voluntary muscle contraction. It's going to receive signals from our proprioceptors throughout the body. So this is going to be regarding muscle tension, tendon tension as well, and joint position. So how much stretch is put on something, as well as those visual cues and equilibrium pathways. So visual cues are really important as well. If you've ever tried to, like balance on one leg with your eyes open, it's difficult, but it's doable. If you really want to test yourself and see how good your balance and equilibrium are, then close your eyes. We're not getting that visual information about where our body is in space, so it's having the muscles are having to work even harder, and it's a really difficult exercise. These pathways continuously are going to inform the cerebellum of our body's position and momentum. So it's not just a one-time, here you are, that's all you need to understand. It's going to continually give us that information. Then the cerebellar cortex is going to calculate the best way to coordinate that muscle contraction smoothly. So things like force, direction, and extent of the muscle contraction to prevent, like overdoing it, maintaining our posture, and ensure smooth coordinated muscle movements. So if you've ever, let's say, try to shoot a free throw, you put a lot of force into it, you don't make the basket. It might hit off the back of the rim or hit off the backboard and then bounce right back out. So after that, your body learns, how much force do I need to actually do this? So that's where that information comes from. Then what happens is it's going to send this blueprint. So how you did it and how it was successful, this coordinated movement, to the cerebral cortex and the brainstem nuclei. So the more you do these things, obviously the better you get at controlling the force, the direction, the muscle contraction that's needed. So initially you might be using, way too many muscles or way too much muscle contraction or different groups of muscles. So this is where we're going to kind of pare that down and just say, okay, here's what I need to use, and we can let all of this other stuff go. So I think one of the best examples is, like, have you ever tried to open a jar of pickles? This actually happened to me the other day. I was trying to open this jar and it was stuck on there so tight. So what is one of the first things that we do? We kind of bring it closer to our body, use accessory movements like using a lot of shoulder movement. You might even bend over at your core and try to use that to help you, use as much muscle force as you can to open it. And then after that, once it's already open, we know that it's there. So we don't have to put as much effort into it. Then it's simply just using a little bit of a turn of a wrist to perform the same movement. So it's also thought some neuroimaging is going to suggest that our cerebellum may also happen to play a role in thinking, language, and emotion. The same thing as it does for motor process is it can compare what it actually, like what it thinks should happen to what actually the output is, and adjust that accordingly, which is pretty cool too. So it's kind of like just like autopilot compares like the plane's instrument readings with how like the expected course of the flight. The cerebellum continuously compares our body's performance with what our brain's actual higher intentions are, and sends out these messages to initiate the appropriate corrective measures. So if we injured our cerebellum, it's going to result in a loss of muscle tone, and probably going to have some clumsy and uncertain movements as well, or not smooth coordinated muscle patterns. So that is the end of sections 12.4 and 12.5.